Um, so welcome everybody for this webinar, and as supported by the UNESCO IGCP project 636 phase 2 geothermal resources for energy transition. We will be presenting the webinar for Geotheroom for Algeria. So mainly we will have discussion about the different sources of geothermal energy in Algeria. We will have presentations from different participants from École Nationale Polytechnique of Constantine and other institutions as well. So we will talk about them later. So basically, this webinar or this project includes different countries from different continents. And as you can see here in this slide, we have Colombia, Mexico, Iceland, Algeria, France, Canada, Slovenia, Spain, Sweden, and Italy. And for each month, there is a country who is taking part to present their resources and the different studies that they are carrying out in their country. As a leader, as a leader institution in Algeria, so it is École Polytechnique de Constantine, and the project manager representing Algeria is Dr. Hamza Sammari, who is present with us. We are also 4 members participating in this project, myself and also Dr. Abdel Hakim Jabara from École Nationale Polytechnique de Constantine. We have Dr. Soufiane Aberkan, assistant professor at Guelma University, and also Fouad Bouisha, associate professor at University of Constantine I. So for this webinar, as I said, we will have different talks, and I will start myself by doing a brief introduction. So in this introduction, actually, I will talk a little bit about Algeria. So maybe for foreign people with us here, they will know a little bit about Algeria, our history, and also some traditional things that we would like to share with them. Then we will move forward to renewable energy in Algeria. We will present also some highlights about the master thesis that have been carried out about geothermal energy in École Polytechnique de Constantine, and also in Guelma University and other institutions as well. Then we will show a brief description of the workshop that have been carried out in the École Polytechnique de Constantine about the ArcGIS software. And at the end, we will move to different presentations from our colleagues. So each of them will present a different topic about geothermal energy in Algeria and its application. If we talk about Algeria, basically is the largest country in Africa and the 10th largest country in the world, with an area of about 2.3 million kilometers square. And 70% of this area is covered by the desert. So as for the population, till now we have about 45 million, that most of them are living in the north part of Algeria. So the average density is around 80% by kilometer square. The main industry in Algeria actually is oil and natural gas. So going to the history of Algeria, Algeria is located near Europe and it was frequently invaded for centuries and governed by like Spanish, Turkish, and French. So the last one was French from 1830 to 1962. Revolution of nationalist resistance has been conducted by the National Liberation, leading for the independence in 1962. So this is the flag of Algeria. with two colors, green and white, and we have also the crescent and star, which is a symbol of Islam, which is the major religion in Algeria. Actually, 70% of people live in the cities along the coast in the north part of Algeria, and the official language is Arabic, and the chief religion is Sunni Muslim. Also, the currency is Algerian dinar. So you can find also that Algeria is a very rich country in terms of diversity. So each part has some specific, foods and very famous food like couscous, pasta, chicken, lamb, and vegetables. And you may enjoy the food in Algeria in different places. Also for the dresses, it's really rich of different cultures. Like for this, in the cities, they wear like Western style clothes, and men wear business suits with hats that we call fez. Women wear dresses, but some cover their faces with a veil. And also we have Berber women who wear like blouses, skirts, and shawls with flower patterns, as you can see in this figure here, for example. We do have also men who wear, as we call, barnos. So it's really different dresses in different parts of Algeria. So this is like, it was a brief about our country, and now we will move forward to the renewable energy in Algeria. So basically, as you can see here in the left figure, the main resources is natural gas with like more than 64%. Also, we have the oil like for 34%, and the remaining is just a very small percentage of using renewable energy and coal. So basically, the plan for 2013 is to investigate in different renewable energies like photovoltaic as a main resource, because as I said first, Algeria is covered by about 70%, more than 70% as a desert. So we have the photovoltaic resources, wind energy, biopower, a little bit of geothermal resources, and also CSP. So basically, the National Renewable Energy Program target is based on four main points. The first one is the construction of electricity production plants from renewable energy sources. The first objective from the Ministry of Energy Transition and Renewable Energy is to achieve 1,000 megawatt cumulatively per year. That means that at about 2035, we should have like 15,000 megawatt produced electricity from renewable energy. So this is the plan from the Ministry of Energy Transition and Renewable Energy. The second point is preparatory work for the launch in 2021 of 1,000 megawatt in photovoltaic solar power plants. This includes mainly the creation of renewable energy development company, update of prospecting studies for land intended for renewable energy project, and also identification and removal of constraints like financial, legislative, technical, and administrative constraints that each project may face. So the objective is to reduce these constraints. The third point is identification of the national renewable energy potential. So basically, there will be a registration of budget allocation for 2021 financial year for financing 10 studies. These 10 studies includes 3 studies for installation of photovoltaic solar power plant, 5 studies for the establishment of wind farms, and 2 technical studies for the analysis of the operating results of pilot power plants. One is 1.1 megawatt photovoltaic pilot plant, and in Ghardaia, this is a city in like the south of Algeria, and also a 10.2 megawatt wind farm in Adrar. Adrar also is another city in the south of Algeria. So the last point is development of renewable energy applications, and this includes the developing geothermal energy, developing hydroelectricity, and contribute to the promotion of product of applied scientific research in the field of renewable energies and energy efficiency. So basically now I will move to the different master theses that have been carried out in École Nationale Polytechnique of Constantine, and also University of Guelma, and I will give a summary of them. So the first master thesis that I had the honor to supervise is titled Numerical Simulations of Heat Exchanger in Deep Borehole Drilling in Geothermal System, Application in the Algerian context. So we have had 2 students that carried out this master thesis, Marwa Safir and Rania Hamouda, and the objective was to simulate numerically the borehole with different shapes. So we have like conventional U-tube, and also U-tube for borehole with fins, like internal fins here. And we have another shape, which is helicoid tube. So we compare the different geometries to get the best performing one, and the one that's provide a better heat transfer rate. So this is basically the mesh we have used, where we have refined the different places to where the gradient are important. And we validated and compared our results with previously published data. So in this borehole, basically we have cold water that enters the tube, and from the heat that we get from the geothermal resources, the cold water will get heated, and then we can get like an outlet higher temperature that can be used in different applications later. So basically these are the results where we compare different the different geometries, like the U-tube case and the helicoid tube. And we can see that the temperature is increasing from the inlet to the outlet. We investigated also the comparison between the simple U-tube and the U-tube with fins, and we have seen that including these fins will increase the temperature of the outlet water. Also, we investigated different helicoid geometries by investigating different mass flow rates, and also different step between the helicoid geometry. These are the different conclusions we get from this study, where, for example, decreasing in the diameter of the helicoid increases the temperature of the water at the outlet. Decreasing also the water mass flow rate at the inlet of the helical tube increases the temperature at the outlet. And we found out that the best performance for the output temperature was for the case of smallest step of about 0.1 meter. The addition of fins increases also the heat exchange surface area as well as the outlet temperature, and decreasing the decrease in water mass flow rate at the inlet of the U-shaped fin tube increases the temperature at the outlet. So there is another master thesis that have been supervised by our colleague, Dr. Abdelhakim Jabbara, and is about design and sizing of a Benki turbine. Actually, this is the design that have been developed, and also they were able to construct this turbine at the École Polytechnique of Constantine. And this turbine basically can be used in the superficial water, like shallows. For example, if you have a high shallow, this water can be this turbine can be included below the shallow, so it will produce the electricity at the end. They did several investigations of different parameters to compute like the net height, the torque and efficiency as function of the turbine speed. Another thesis entitled Economic Study and Mapping of Algerian Geothermal Potential for Electricity Production, which is supervised by Dr. Hamza Sammari, who will give us a talk later, and maybe he will give us more details about this thesis. I'll give him the opportunity to give us more detail. We have another thesis carried out by and supervised by Dr. Soufiane Berkan, who is also who will also present in this panel. So the thesis title is Study and Sizing of Geothermal Energy Heating System for Xana Thermal Spring in Buera. So he will be able to give us more details about this later as well. Also at the École Nationale Polytechnique de Constantine, we did a workshop about ArcGIS software, and thanks to our colleague who will present also later, Dr. Fouad Bouisha, who actually managed to do this workshop, and actually we invited different students at different levels, also some colleagues also who participated, and we really enjoyed this workshop, and we learned a lot about this software that can be useful for any applications of geothermal or other applications as well. So you can see here, this is the workshop that take place at the École Nationale Polytechnique de Constantine. I think now I came to the end of this introduction, and maybe we can move now forward by the next presentation, which should be by our colleague Fouad Bouisha. He is associate professor at the University Frère Montory Constantine I, and the talk will be about the Algerian geological and hydrogeological context. And maybe before going forward to this presentation, I ask everybody, if you have any questions about the introduction that I just gave to you, please feel free to ask any question, and I'll be happy to answer them. So if anyone has any question about what I have presented, please feel free.
I've just sent a question in the chat.
Yes, just let's see, chat. What software have you used for the numerical modeling of the different configuration? Yeah, actually we used ANSYS Fluent for the simulation of the boreholes.
Okay, thanks.
Yeah, welcome. Thank you. So we have also planned to do design of other geometrical boreholes, and also to get like more optimized geometries using different parametric studies. And maybe these boreholes can be used, you know, for like heating the water, for example, and especially in the area where we have some hot water resources. We have here some cities like Guelma, like, you know, in the east or even in the west part of Algeria that have these resources, and we are planning to do some investigations of using these boreholes in the heating of water, like that people can use in their houses. Okay, I think if there is no question now, we can move to the to our colleague. Fouad, you are here. I'll stop sharing
Bonsoir,
my
oui.
screen. Bonsoir. Fouad.
Oui, je suis là.
Okay,
Est-ce que vous m'entendez bien?
Yeah. Wait. I'll
Ouais.
give you just a minute. I'll give you the right to so you can share your screen.
Okay.
Just a minute. Okay, can you try for Ed to share your screen now? Yes, we can see your screen now.
Activer le son. Bon, bonsoir tout le monde. C'est Abdelkader. Vous pouvez
Yes.
faire les conversations vers l'anglais. Bon, aujourd'hui, je vais représenter, je vais faire une présentation concernant le contexte géologique et hydrogéologique des ressources géothermales en Algérie. Concernant notre présentation, et s'articuler sur 5 points essentiels. C'est la géologie de l'Algérie, l'inventaire des différentes ressources géothermiques en Algérie, la distribution du gradient géothermal ainsi que le flux, la présentation de certains réservoirs géothermiques et enfin en conclusion. Est-ce que
Okay.
tu fais...
I think Fouad, maybe you can continue with French, and as your presentation is already in English, maybe I think most of people here maybe can understand French, right? Daniela, can you understand
Yes,
French,
oui,
right?
oui, pas de problème. Ça fait, c'est parfait.
Ah, donc
Okay,
c'est
so
génial. Ouais.
yeah, no problem. If as your presentation is already in English, so I think everyone can understand and read a little bit. But later I can explain if they have some questions. I can explain them,
Ok,
for example.
ok,
Yeah,
pas de problème.
just go
Ouais,
ahead.
ok.
Yeah.
Ok, merci. Bon, concernant la géologie de l'Algérie, en premier point, les ressources géothermiques en Algérie sont de type de basse enthalpie à moyen dans certaines régions. Il existe dans notre territoire plus de 280 sources thermales. C'est-à-dire cette distribution est distincte entre deux zones, la partie nord et la partie sud. Bon, on peut diviser les provinces géothermiques en Algérie en 3 provinces. La province Est et l'extrême Est, c'est-à-dire où il y a la région la plus importante de point de vue géothermique. La partie centre et la partie ouest, c'est la région de Tlemcen où il y a les Dolomites. Et la partie sud où il y a tout ce qui est aquifère, albien, et ainsi que certains bassins comme le bassin de Tindouf. Ce qui concerne la partie est, c'est la zone la plus complexe. On a trois grandes divisions structurales où il y a les zones internes, les zones médianes où il y a les flyschettos et la zone externe où il y a les nappes. Bien sûr, en Algérie, on a un contexte un peu spécifique où il y a l'empilement des différentes nappes, où il y a, c'est ce qu'on appelle en géologie les chevauchements. Donc, c'est la zone la plus complexe de notre territoire algérien. Bien sûr, il y a aussi la plateforme saharienne, c'est après ces trois zones-là. Un aperçu ou bien une présentation plus simplifiée où il y a les griffons principaux, où il y a 280, plus de 280 dans les derniers recensements, sur la totalité de la partie nord, beaucoup plus, et une deuxième présentation plus au sud où il y a le bassin, une partie où il y a le bassin, c'est-à-dire la nappe albienne, et après on a, c'est-à-dire le massif d'Agga. Concernant la répartition des différentes températures, c'est-à-dire on a des températures qui passent de 22 degrés jusqu'à 96 degrés Celsius au niveau des griffons, où l'application de la géothermométrie est spécialement dans la partie est, elle nous donne avec les géothermomètres de gaz la température des réservoirs à peu près c'est 198 degrés Celsius, et les géothermomètres quartz plutôt, c'est à peu près c'est 120 jusqu'à 140 degrés Celsius. Les applications généralement utilisées en Algérie, c'est au niveau de la balinologie, l'aquaculture et certaines applications comme vous voyez après avec nos collègues, l'application de la production d'électricité et surtout le projet pilote à la wilaya de Saïda. La distribution du flux et du gradient. En Algérie, on a une moyenne de 30, c'est-à-dire de 30 degrés par kilomètre. Les parties les plus importantes sont des parties, c'est-à-dire réparties à l'extrême est et à l'extrême ouest, ainsi que la partie de la région de Tindouf, ainsi que la partie du sud de Timimoun, c'est-à-dire au nord du massif de Haga. L'origine généralement du gradient géothermique, c'est-à-dire comme connu, c'est le noyau, l'activité radioactive et l'activité tectonique. Et ce point-là, le dernier point, c'est l'activité tectonique, c'est un point très important, surtout dans la partie est où il y a une activité sismique ainsi qu'une fracturation intense dans cette partie-là. Bon, c'est des généralités. On passe vers la prochaine. En Algérie, on peut diviser le secteur, notre pays en 5 zones très importantes, ou bien 5 provinces, sous-provinces, area. La première, c'est la zone la plus importante de point de vue géothermique et la plus, où il y a une densité importante de point de vue ressources au niveau de la surface. où il y a les différentes sources principales comme Tassa, Zaïd, Bni Salah, Zatout, Hammam Belhachani, Hammam Girfa, Hammam Beyl aussi, et la région jusqu'à la région de Khenchela. La zone la plus importante, vous la connaissez tous, c'est la zone de Guelma. Elle se situe au centre de cette zone-là. La deuxième zone, c'est la zone des Bibans et les Babors, c'est-à-dire Est-Centre, où il y a une extension plus ou moins allongée du nord vers le sud, le Biban, les Babors, jusqu'à la partie des Aurès, et limitée par une partie des Hodna, la dépression des Chott. La partie centre-ouest, elle est localisée par principalement ou bien marquée par le bassin du Chilif, où il y a une activité importante sismique, où il y a aussi une activité ancienne de certains volcanismes, c'est-à-dire plutôt c'est une activité plus ou moins récente, c'est-à-dire c'est-à-dire la zone l'âge Méocène, où il y a par exemple la dépression de Zahras qui est située ici, jusqu'à le bassin de Chlef. De manière générale, c'est ça la zone où il y a une importante source thermale, mais avec des températures plus ou moins moyennes à basse température. Bon, la partie extrême ouest, elle est marquée par les plaines de Mrnia, avec une extension jusqu'à Tsefna et Benessaf à la partie ouest, où cette zone est marquée par une intense fracturation transversale, et cette zone marquée aussi par les manifestations volcaniques. La dernière partie, c'est la partie sud. Une partie de la région, il y a une certaine anomalie ici à la région de Tindouf, et la principale, c'est l'Albien, ou bien l'aquifère intercalaire de l'Albien, où il y a la plus grande nappe dans le nord d'Afrique et même dans le monde presque, avec un potentiel important, avec des températures moyennes de 65 à 60 degrés Celsius. Vous voyez ici une répartition des températures des différents greffons, avec certains forages dans la partie sud, surtout à Biskra, ici à Rtaya, Ouergla et Ouetsouf. Vous voyez le fond de la carte où il y a un gradient géothermique important, donc une répartition, une coïncidence entre l'importance du gradient avec celle des températures. La même chose pour le sud. Vous voyez ici le bassin de Tindouf, vous voyez ici Adarat, Mimoun, Reggani et tout. Donc, vous voyez une partie importante, c'est la zone où il y a le bassin, la nappe aquifère albienne. Bon, ici, une répartition quantitative. Donc, la plupart des sources, c'est avec des basses températures en moyenne, entre 22 et 45. Après, suivi par d'autres moyens, ce qui est en jaune. Et la partie la plus importante, c'est la partie est, où il y a une forte concentration des températures très élevées qui atteint les 96 degrés Celsius à la surface. Bon, certains réservoirs géothermiques en Algérie, on a plusieurs, on a cité quelques-uns, les plus importants. Hammamet de Tbessa à l'extrême est, la région de Guelma, c'est le bassin le plus important. Aussi, on a la partie du Hadna. Moussaran aussi, c'est un réservoir très important. À l'extrême est, l'ouest algérien, avec le réservoir de l'Oranais, et le Sahara représenté par l'Albien, l'aquifère albien. Ici, j'ai mis deux exemples. Les plus importants, c'est Hammam Dbar et le réservoir de Dbar et le réservoir de l'Oran. Donc, vous voyez des températures, c'est-à-dire la répartition des sources les plus importantes dans la région, avec sa relation avec l'activité tectonique ici. Et cette zone qui présente, c'est-à-dire les températures les plus élevées, avec des anomalies proches aux zones volcaniques, avec des températures avant les 2003, des températures qui atteignent les 98 degrés Celsius, mais maintenant, c'est-à-dire diminue jusqu'à 96 degrés Celsius. Vous voyez ici un schéma ou bien un croquet où il y a une répartition linéaire des différentes sources thermales et une concentration dans la région de Hammam Dbar où il y a les différentes sources thermales exploitées surtout par soit des vestiges touristiques hérités, c'est-à-dire depuis des années et des années. Et le complexe le plus important dans la région de Guelma, c'est le complexe de Chellala. De manière générale, en hydrochimie, on a deux faciès, le faciès sulfaté calcique et le bicarbonaté calcique, avec des températures où il y a, par exemple, ici, concernant le réservoir, c'est un complexe entre tout ce qui est carbonaté du maastrichtien beaucoup plus, et évaporitique, c'est-à-dire tout ce qui est triacique, gypse, sel, jam, etc., du Trias. Donc, avec un débit très important, stable depuis des années et des années, selon les enregistrements depuis les 1962 jusqu'à maintenant, on atteint les 1200 litres par minute. Juste dans le plateau, donc dans d'autres zones, s'il y a un cumul, elle dépasse les 1200 litres par minute. Donc, toutes les sources, il y a des témoins, c'est-à-dire de minéralisation, surtout en minéraux lourds, qui nous donnent l'impression qu'on a un réservoir très profond, qui est c'est-à-dire dans nos études, il atteint les 2 jusqu'à les 3 km en profondeur. Dans la partie ouest, c'est-à-dire dans le réservoir de l'Oranais, selon la dernière étude faite par Belhi en 2022, on a un potentiel aussi plus ou moins important, avec des faciès un peu différents que les autres. Vous voyez après avec Madame Zerroqi. La plupart c'est un mélange entre tout ce qui est critacé et tout ce qui est carbonaté. C'est-à-dire, vous avez tous ici le NaCl, le NaHCO3, c'est-à-dire le bicarbonaté sodique, les chlorures sodiques, les bicarbonatés calciques et les sulfatés sodiques aussi. Les débits sont plus ou moins médiocres, entre 6 et 9 litres par seconde, avec des températures qui ne dépassent plus les 68 degrés Celsius. Par contre, à la région est algérienne, on a des simples, c'est-à-dire des simples griffons abandonnés déjà avec des températures qui atteignent les 75 degrés Celsius. Bon, voilà un concept, c'est-à-dire un modèle conceptuel de la partie ouest. Vous voyez ici le réservoir, c'est-à-dire principal, c'est le Trias, avec celui-là, le Crétacé, c'est-à-dire les carbonates. L'intercommunication entre les deux nous donne, c'est-à-dire les différentes circulations, ici les différents greffons ou bien différentes sources principales. Bon, en conclusion, l'Algérie, avec un héritage très important du point de vue thermal, plus de 280 source et qui est présent des températures aussi
I think there is an issue with sound, right?
Yes, it is.
Yeah, maybe it's internet connection problem
96
sometimes.
degrés Celsius. Et on a parti et les jours qui géologiques.
To add, I think there was a problem with the Fuad, can you hear us? Yeah, I think he has a problem with connection, but we are lucky that maybe he almost finished his presentation, and hello, Fuad, yes. Connection problem, yeah. It's okay, it's okay. I think you almost finished your presentation, right?
Problème de connexion.
Okay.
Ouais.
Yeah, no
Donc,
problem.
juste un petit point, Abdelkader. Les voies avec les okay, ماشي مشكل.
Well, we can't hear you very well, maybe, but still, if anyone please has question about the Fuad's presentation, please feel free to ask question directly or in the messenger, in the chat room as well. And Fuad is here, can. Okay, let's see the first question from Daniela. Très intéressant, merci Fouad. La nappe de l'Albien est partagée parmi plusieurs pays. La caractérisation de son potentiel géothermique est-elle menée par tous ces pays? Do you have a collaboration with Tunisie et Libye?
Can I answer or?
Fouad?
If Fuad cannot answer, I can.
Fuad, you are here? Can you hear us? Sorry, maybe he still have an issue with his connection. Can you hear us, Fuad? Or maybe, yeah, Mr. Aitwali is here, and maybe he can, yeah, he can answer this question.
Yes, it's aquifer chart between. Dear all, my name is Aitwali. I am head of geothermal team at Renewable Energy Research Center, CD Algeria. Okay, I am hydrogeologist. I will answer you about hydrogeology. The aquifer is shared between three countries: Tunisia, Libya, Algeria. 60% is underground of Algeria, and currently there is a recent study in 70s by UNESCO about management of this great aquifer, and now maybe there is a new project about this transborder shard aquifer. And there is a good high committee level at IEH, International Hydrogeological Association, about cross-border aquifers. Maybe there is currently another updating research about this great aquifer between three countries. And there is in level at Africa other shard aquifers, maybe in the Nile between Egypt and Ethiopia and Kenya, and there is a good other. Okay, but this is a good opportunity to work between three countries. Thank you.
Yeah, thank you so much, Dr. Aitou Ali. So he's the head of geothermal in CDUR in Algiers, the capital. And thank you for your answer. Hopefully, Daniela, you get the answer from him. And if you do have other questions, please feel free to. Yeah, thank you. Any other questions, please? Directly or in the chat room as well, you are welcome. Okay, so if there is no other questions, okay. We do have a question from Benzagota. How can you schedule boreholes or drilling plan towards an overlapping area where the source is known with ambiguity? Fouad, or maybe Aitou Ali.
Yeah.
If you can answer this,
Yeah.
also we will be so happy.
Our
Please.
Professor Benzagota. Yeah, how I read the borehole drilling plan to overlapping area where the source is.
Yeah, his question is basically if you have, for example, area where the source is not really known or there is ambiguity between two adjacent area, how can you schedule a borehole or drilling plan for this?
I can, if we have this some case, we managed to do a good geophysical campaign, magnetotelluric and high geochemistry analysis to locate to see the geophysical, to see geometric of our reservoir and the anomaly, the real anomaly, and the chemistry to see the flowing of our geothermal fluids, to locate them, to take the borehole. Maybe, yeah.
Abdelkader.
Yes, Fouad.
Bon, merci Aitou Ali. Bon, concernant la question de M. Benzagota. Pardon?
Yes.
Yeah.
Yes, go ahead, Fouad.
Concernant la question de M. Benzagota, généralement, l'exploration géothermique se fait sur deux grandes phases. Une phase d'exploration géochimique, hydrogéologique et une phase géophysique. C'est bien sûr comme le pétrole. Donc, on ne peut pas faire un forage quelconque, mais avec des compléments, c'est-à-dire l'étude géochimique, c'est-à-dire elle nous donne, c'est-à-dire les différents modèles de mixage, les différentes contaminations entre les eaux froides, les eaux chaudes, etc. Mais pour faire, c'est-à-dire un modèle conceptuel géologique, il faut passer par des méthodes géophysiques. et principalement par la MT, la magnétotellurique, beaucoup plus, et beaucoup plus tout ce qui est sismique. Sismique, c'est-à-dire pour avoir le point exact de forage. Généralement, il y a plusieurs, dans la première partie, il y a plusieurs d'autres méthodes, comme les méthodes structurales, pour avoir c'est-à-dire une idée sur le modèle structural, les drains principaux, c'est-à-dire de flux, de chaleur, etc. Ce sont les grandes fractures, les grandes failles, et ainsi que les plis où il y a toujours les captages de notre réservoir parce qu'il y a un mixage eau, steam, etc. D'accord.
D'accord.
J'espère bien. Ouais.
Yes, thank you. Thank you for Ed, and thank you also for the participants for their questions, interesting questions. Maybe now we should move to the next presentation, which is actually which will be presented by Dr. Siham Zerro from ASGA, which is Agence du Service Géologique de l'Algérie. Please, Dr. Siham, you are free to share your presentation, and please start whenever you are ready.
Okay, we can please.
Yeah, we can hear you. You can share your presentation, please.
Can you see the presentation?
Not yet for me.
Maybe. I don't know where is the problem exactly.
Otherwise, if you have an issue, I don't know, maybe you
yes,
can
I have an issue.
If you can quickly send your presentation maybe to Hamza,
Okay.
and he can share it from his.
Yes, it's okay.
I
can do it.
Yeah, please.
Okay,
maybe in the same time, we have another question. Let's get benefit from this question till Dr. Siham figure out the problem. Benzagota is asking for the northeast of Algeria has got outcomes from updated seismic are with uncertainty. Fuad, maybe you can answer this question the time that Dr. Siham will figure out the problem with this screen sharing. Fuad, you are here?
Abdelkader, répétez la question, s'il vous plaît.
Mr. Benzagota said that the northeast of Algeria has got outcomes from updated seismic are with uncertainty.
Oui, toujours. Bon, dans l'Est algérien, comme il savait, il y a des problèmes avec, c'est-à-dire ces techniques-là, parce que ces techniques sont très coûteuses et tout le monde n'a plus le droit de consulter les résultats, de consulter les modèles, etc. Parce que c'est des modèles confidentiels, c'est des modèles faits pour la prospection pétrolière. D'accord. Il sait bien, M. Benzagota, que ces données-là, faites par Sonatrach, et surtout dans la région de Guelma, le bassin de Guelma, il n'existe plus ce genre. Les derniers temps, peut-être il y a certaines études, mais j'ai aucune idée, certainement. Franchement.
Okay, thank you. Thank you, Fouad. I
see my
think now we
screen,
can
please.
see, yeah, we can see the screen of Dr. Siham.
Okay.
So please feel free to start and yeah.
Okay, thank you. You can hear me, please?
Yeah, we can hear you. Yeah.
Do you hear me, please? Okay. Okay, good morning, everybody, or good evening. My name is Siham Harouk, and I am a doctor of geoscience. Actually, I'm working as an engineer at the Geological Survey Agency. Today, I'm going to present an overview of the geological setting and the geochemical characteristics of some Algerian hydrothermal springs. The order of the presentation is as follows. Non-introduction, the main goals of this presentation. We are going to discuss in this presentation two main points. The first one is the relationship between geology, especially plate tectonics, and geothermal energy. In this main point, we are going to talk about the major structural of Algeria in geochemistry and the geological setting of the thermal waters. Then we are going to discuss some geochemistry characteristics of some Algerian sources. And we will finish by conclusion. So the geothermal energy has been used for several purposes since the Paleolithic period. Algeria has a significant geothermal potential linked to its geological diversity. These potential fields, unfortunately, the actual use of this resource remains very limited in Algeria due to two main problems. The first one is the availability of other energy resource and the high cost of exploration methods. The geological and the geochemical studies can present very powerful tools for the orientation of the exploration and exploitation studies, as well as the identification of areas with geothermal potential. The main objective of this study is to show the interest and the importance of geological thermal sources before any study, I mean geophysics study or drillings or anything else. So the geological and geophysical study can give us an idea and can identify the course of water and the type of aquifer through its geochemical components. And can identify the geophysical method to use for an exploitation, and the estimation of temperature and identification of the origin, whether it's tectonic, chemical, or related to geothermal gradient. Another important point is the prediction of the use of water through its chemical process. As a definition, a geothermal energy is thermal energy used and stored in the air. The temperatures at the core shell boundary reach over 4,000 degrees Celsius, 600 degrees Celsius. In the Earth crust, the flux increases with the concentration of radioactive. The decay of radioactive elements accounts for more than 90% of heat flux. The 10% is the residue of heat of initial formation for 4.5 billion years and coming mainly from the core and the mantle. As we can see in this graph, the evolution of the temperature in the underground, we can see that the average temperature is 100 meters in the upper part of the lithosphere. But there are some interesting zones which we call hot zones. The temperature is about 20 to 30 degrees Celsius every 100 meters. As we can see here, and when I want to emphasize the first point, which is the relationship between geology and the geothermal energy. In this figure, we can see at the upper part of the lithosphere that in general, in the magma rise at the ocean level along the mid-oceanic ridges above the subduction zones, like we see here in the right, above the subduction zones and the strongly extended area, and the hot point, which represents the volcanic areas. So the edge of the continent are divided into passive margin and without much interest in geothermal energy, and the active margin with a big interest in the geothermal studies, like the northern Algerian boundary, which represents at very early age of evolution a result of subduction. So it's very important to make regional studies of the whole area or the whole Algerian territory. So here we are going to see the major tectonic units of Algeria, which is the result of different orogenic cycles, which affected the Algerian territory from the north to the south, like the Alpine orogeny and the Archean and the Pan-African orogeny, which especially affected the Hogar Shield. So we have three main units: the Saharian domain, which represented by the Saharian platform, the Hogar in the east, southeast, and the Eglabieti at the southwest. The last deformation for the Eglab and the Hogar are between the Iberian and the African. We have the second unit is the Atlantic domain, which represented the Saharian Atlas and the Tilian Atlas, separated by the high plains and separated by the Saharian domain by the biggest South Atlantic accidents. And we have the northern domain, which call it the Tilian domain, which have been affected by the Alpine orogeny. We have here an example in the Hogar. The current structure of the Tuareg Shield represented by the Hogar in Algeria was formed during the Pan-African orogeny. The Tuareg Shield constitutes the mobile zone between the West African craton and the East African craton. The Hogar underwent lithospheric thickening with a large curvature of radius. This last is accompanied by intense activity of hotspot type, oolitic, alkaline, or from Cenozoic to Quaternary. So this region is very important because of the tectonic and metamorphic events which affected this region. If we can do a sketch for the Algerian territory from the north to the south, we can see here different interesting zones to do geothermal investigation, like the northern part where the subduction, which represented the result of the subduction between the African plates and the Eurasian plates. And also we have the Hogar Massif, which is very important to now that there is cratonic bulging in this part of Algeria. So it's very important to do a geothermal investigation. And we have this part between the Atlantic domain and the Saharan platform. I think that the studies must or have been made exactly in these areas, because there are lots of hydrothermal sources. So the geological study show us that there are lots of a region where we can do our studies, like the hot areas, the boundary of tectonic plates, like the northern part, the subduction zones, and the continental rifting, like the Hogar. So it's important to bear in mind that the regional geological study gives us an idea of the most important zones to focus our future studies, like the northern part, the Hogar Shield, and the Saharan platform. The second point I want to emphasize is the geochemistry of thermal water and their relation to the geological setting. So the cation and generally the geochemical indicators can give us a lot of information. We are going to quote some examples, like the dissolved gas. For example, the dissolved oxygen. The high dissolved oxygen content is typical of water that has had little contact with organic matter or sulfide minerals. The second one is the methane and the hydrogen sulfide. We can see that the nitrite and sulfide suggest the possibility of human influence in the composition of water. It's very important in this case to do a geochemical analysis for these two elements to see if there is an eventual pollution. The third very important element is the helium concentration. They have been observed that there is a close correlation between helium level and the proximity to the hot spring in several locations. The effect was attributed to the escape of helium from the hot water into the local soil gases. Heat and helium are generated during the radioactive decay of uranium and thorium minerals. The decay of uranium 238 into stable Pb and helium release 3.4 per 10 power 10 calories of heat per gram of helium created. The calculation based on this data show that the heat produced by the number of decay events required to add 1 milligram helium by liters is approximately 35 per 10 power of 3 calories. If all this heat were absorbed and retained by the water, its temperature would rise by about 35 degrees Celsius. In an aquifer bed, that in an aquifer system, much of this heat is dissipated by conduction in the aquifer material itself. So the observed temperature rise will be less than 35 degrees Celsius. However, a high dissolved helium concentration is always an indication of an underground heat source consisting of a concentration of radioactive minerals in or near the aquifer and independent of the water circulation depth. Another element very important element in geochemistry is the isotopes, like the oxygen and the carbon, that indicate the type and the extent of chemical reaction between groundwater and carbonate mineral. Tritium has a relatively short life. It's very important to do tritium analysis before anything to see, because this element can give us a relative age of the water, and can give us an information about if there is alimentation of water or not. So therefore, water without tritium and dissolved oxygen has an age greater than 20 years. So the recharge is low, so we can call the aquifer as fossil aquifer. So the isotopic ratio of groundwater oxygen can be modified by chemical and isotopical exchange reaction between water and aquifer rock. Because of the O18 value of rock forming minerals is strongly positive. Reactions between water and the rock will make the O18 value of water more positive. Such reactions occur only very slowly as compared to below 100 and 200 degrees Celsius. Thus, abnormally positive value of O18 may indicate that groundwater has been exposed to high temperature. This is a very important information. So we are going here to talk about the relation, the origin of temperature in the different provinces of Algeria. For example, the Saharan platform, the thermality is linked to the geothermal gradient. In the Saharan Atlas, it is generally linked to the anticline and the syncline present in this region. The Saharan Atlas, especially in the eastern parts of Algeria. In the Italian domain is the result of the subduction zones, and in general, the springs outcrops at the level of the north-northeast fault. So it's very important to do a structural mapping before anything else. In the Hogar, the temperature is generally linked to the Cenozoic volcanism and the high basement. I want to emphasize the point here in the Hogar that the water is there is a lack of water, and generally the aquifers there is just represented by shallow water tables, and their temperature is linked to the Cenozoic volcanism. The example I want to talk about, the example of source in the Hogar. So as definition, the Hogar is a region with a Precambrian basement. The geological structure of this basement corresponds to an amalgamation of several terrains of very different age and history. The latter is surrounded by a Paleozoic sedimentary cover. The rocks of the region are of nature volcanic, metamorphic, and intrusive plutonic. Some chemical analysis carried out of some sample from a few resources in the Hogar show a low content of all ions like sulfate, calcium, and magnesium. It is because of the crystalline nature of the rocks in the region and the relative brevity of water inside shallow reliability also would explain the low level of all those elements. The relatively significant concentration of HCO3 will be related to the release of CO2 gas linked to manifestation of Cenozoic volcanism. So in this case, for example, we know that there was volcanic activity in the area. So it's important to do the HCO3 analysis. This is an example of sources in the Saharian platform, like we see here. The general, there are two main chemical phases: the weakly mineralized and the medium to strong mineralized. The first group, the general weakness of concentration of the various ions, with nevertheless the predominance of chlor and sulfate, sodium and HCO3, indicates a shallow reservoir. This is a very important information to see in this case of this shallow reservoir contains is constituted with poorly soluble nature. For example, the sandstone and clay sands of continental intercalare. The second group is represent the medium to strong mineralized water. It is characterized by the piezometric level, which is very close to the surface and promotes evaporation. Then it's close to the natural outlet shot or sebha. So we can see the influence of evaporative rocks and the importance of the presence of sodium, chlor, and sulfite. There is another important point. By the carbonate reservoir, some elements are specially related or linked to carbonate reservoir, as we can see in this point. The low calcium and magnesium mineralization, more or less than carbonate reservoir rich minerals sites. So in conclusion, the detailed geochemical and geological study on the hydrothermal springs will allow us first to estimate the reservoir origin. The second point is to estimate the water age and the recharge. The type of reservoir can tell us about the depth, as well as facilitate the geophysical surveys and the positioning of drilling. The preliminary orientation of the needs in terms of hydrothermal station, and the last point is the orientation of the future geophysical investigation. I want just to emphasize a point about the geological study. I think that regional geological study and after that local geological study is very important to do these two studies before any geophysical study. Thank you for you, and I'm very happy to be with you today. Thank you.
Thank you, Dr. Siham, and it is our pleasure as well to have you with us here in this panel. Thank you also for the nice presentation and the different informations you shared with us. And now maybe we can go to the questions.
Yeah.
Please feel free, anyone, if you have a question about Siham's presentation. Directly, you can ask your question directly or in the chat room as well. Okay, we do have a question from Daniela. She said, thanks about the last point you showed in the conclusion. Sorry.
What exploration geophysical methods are mostly used in Algeria?
In Algeria.
I think that well, it's different from a study to others. I want to say that if we have a geological study of geothermal spring, we can use the magnetotelluric, we can use the aeromagnetic and aeroradiometric exploration. Also, as I said in the presentation, from the north to the south, the geological setting is very different. For example, in the south, there are much more magmatic rocks or volcanic rocks, but in the north, there are more sedimentary rocks. So if we are going to study sedimentary rocks, I think some electric methods are very useful in this case. But if we should study in the Hogar, we can use the magnetotelluric or the aeromagnetic methods. So it depends on the study and the needs.
Okay. Thank you, Dr. Siham. Yeah. Any other questions, please? Okay. Yes.
Add some words. Sorry, can I add one?
Yes, sure.
Half minute to summarize what she told my colleague Zaro. To summarize, for deep anomalies, we want to use directly anti-magnetotelluric to locate the deep anomalies, and when we want to study up the surface, the uprising, the condition of rising of our heat sources, I think it's good to tomography, subsurface tomography, subsurface geophysical methods. The empty for deep reservoir.
The deeper one, yes.
And it's good, cheapest, the aeromagnetic.
Yes.
Thank you. Yeah, thank you for additional information, Dr. Aitwali. Thank you, everybody. Thank you again, Dr. Siham. And I think we can move now to the next presentation. Please close your sharing. So yeah, the next presentation is by Dr. Hamza Sammari from the École Polytechnique de Constantine, entitled Valorization of the Geothermal Resources for Electricity Production, Case Study for Chellala Thermal Spring in Guelma. Hamza, please, you can start whenever you are ready.
Okay, thank you, Dr. Filali. Yes, I'm already ready, and I will start. Just 1 second. Yes, it's okay now, right now. I think also that I will stop my video to be sure that my voice will be in a good shape. Okay. Yes. Okay. Good morning, good evening, good night, everyone, depending on which country you are following us. I am Dr. Hamza Sammari. I am an associate professor at the École Nationale Polytechnique de Constantine. I am a member of the Mechanics and Advanced Energy System Laboratory, as well as the NGO Energy Cities Algeria. My presentation today deals with the valorization of geothermal resource for electricity production, which is a case study for the Chellala thermal resort, or what we call commonly here in Algeria, Hammam Chellala. Yes. Okay. This work was performed in the framework of the UNESCO IGCP 636 project, which is titled Geothermal Resource for Energy Transition. And the main idea of the present project is to foster and promote the valorization of geothermal energy for different applications such as heating, electricity production, as well as cooling. Those applications are also considered as pure ones in the Algerian context, especially for the case of the thermal resorts. And that's why we are working on it. Okay. The project includes a consortium of 18 countries representing the 5 continents, and Algeria is officially represented by the École Nationale Polytechnique de Constantine and the Center CDR. And the main idea here is to share knowledge, experiences, and also to support developing the country. The Algerian researchers involved within the project are working on 4 pillar topics: inventory and exploration, electricity production, heating, and cooling too. So why do we work and consider the geothermal energy? The answer is that the geothermal energy is a renewable resource. It is widespread in Algeria, as already presented by Dr. Baisha, with a higher potential, especially in the northeast region, which is represented by Guelma. Geothermal energy is stable and non-variable energy in like solar and wind energies. In other words, geothermal energy doesn't depend on weather conditions. It is available day and night and throughout the year. And this is the main advantage of the geothermal energy. Based on temperature levels, geothermal energy can cover several applications as resumed in the present modified Lindell diagram. And when taking into account the available Algerian data, we can say that suitable applications are those requiring a temperature of less than 100 degrees Celsius. In this context, we remark that even electricity can be produced, since we still at the lower limit of power production area. However, this requires to choose the right power plant technology. Good. And the geothermal power plants can be divided into main categories. The flash geothermal power plant that you can observe in these slides. And this technology requires higher temperature of more than 200 degrees Celsius and with an output capacity of a range of megawatts. The second category, which is the most important for Algeria, is the binary geothermal power plants. By the way, the word binary comes from the 2 loops of the system: the geothermal loop providing heat, indicated here in blue, and the ORC loop in charge of converting the geothermal heat into electricity. Such technology operates under moderate to low temperature levels, generally less than 200 degrees Celsius, and such power plants can deliver capacities ranging from kilowatt to megawatt hour output. As the Algerian geothermal resources are characterized by temperature levels lower than 100 degrees Celsius, the binary and especially ORC power plants seem to be the most adapted technology for electricity production. The ORC technology is very mature and largely used for geothermal application over the world, as you can observe on this map, with interesting concentration in European and North American continents. Africa count limited application, and no application unfortunately exists in Algeria besides the important potential of geothermal resource in this country. Consequently, we decided to investigate the feasibility of the ORC system to produce electricity for the case of Chellala thermal resort, or Hammam Chellala. And our selection of this site was mainly based on its highest temperature of about 100 degrees Celsius. The thermal resort presents also in interesting proximity of both production and energy demand. That means that no additional investment will be required for electricity transportation. In addition, the thermal resorts are very suitable for geothermal application, such as heating, cooling, as well as electricity production. The current use of the geothermal resource is based on collecting the geothermal water at 97 degrees Celsius, pumping it into a cooling pool until reaching the temperature of 47 degrees Celsius. And after that, the cooled water is transported towards the thermal resort for the balneology application. The previous cooling process resumed here point out clearly the wasted heat energy that can be recovered advantageously to produce electricity. And this can be made possible by integrating the ORC system as depicted now. The idea here is to exploit firstly the ORC system to produce electricity before sending the geothermal cooled water at 47 degrees Celsius towards the thermal resort, with the constraint that we have to respect, which is the temperature of 47 degrees Celsius, to avoid any disturbance of the operating mode of the thermal spa or the hammam. In this way, an electric output power of 250 kilowatt was obtained. After that, and in order to ensure a good integration of the ORC system, we have carried out an energy audit for the thermal resort of Chellala. And the aim was to address its energy demand profile and point out also recommendation to ensure that the integration of the ORC system will be performant in the good condition. The first recommendation was to shift to the consumption from peak to night or off-peak hours with a substantially saving of $900 per year. And here I just underline that such action is an energy management measure and doesn't require any investment. Later on, the analysis of the energy demand profile highlights that the subscribed maximum available power of 650 kilowatt can be reduced until a value of 500 kilowatt, since the maximum absorbed power identified here doesn't exceed 490 kilowatt. Consequently, the second tips recommend the reduction of the maximum available power with direct energy saving of about $320 per year. And in the same way, such measure doesn't require any investment since it's considered as an energy management action. And finally, the ORC system was expected to, as the third measure, allowing the reduction by half of the dependency of the hammam Chellala or the thermal resource in terms of maximum available power towards the national electricity grid. In fact, the ORC system allowing additional reduction of about $430 per year. And contrarily now to the measure 1 and 2, the ORC system is heavily investment measure and profitability of its integration should be investigated. Now we can resume the combination of the three previous solutions. It will lead to an annual energy bill reduction of about $1,700 per year. And this is represent an amount of 4% compared to the annual bill. This small reduction is mainly due to the large subsidized price of electricity. And normally we will get more than 4%. Additionally, we have tried to investigate the profitability of the ORC system integration presented previously at the third measure and obtained results based on subsidized electricity price of 4 Algerian dinar per kilowatt, which correspond to $0.03 per kilowatt hours. And this will lead to a payback period of more than 28 years. That means that the system will not be profitable at all within the Algerian context. However, we have done sensitivity analysis when we were varying the price of electricity, and profitability becomes somewhere interesting when the subsidized or subsidies are removed and the payback period of 7 years were obtained when considering a production price of 16 Algerian dinars. That means that this price corresponds in reality to the levelized cost of electricity, and this gives an interesting payback period, which was fixed at 7 years. The key finding here is that the subsidies of electricity prices must be removed partially or even totally to make such integration interesting from the economic point of view. Otherwise, the Algerian politic or strategy with regard to energy transition will fail. Good. As conclusion now, this case study has allowed us to demonstrate the technical feasibility of the ORC system for the electricity production. Unfortunately, such a solution is not profitable within the Algerian context because of the subsidies of the price of electricity. And further works should focus on the improving of the economical study, removing the different assumptions that we have considered through this study, and maybe think about optimization or even the hybridization of the system. And finally, I would like to thank you for your attention, and many thanks also to our partners and my former students, Amal Hajri and Noor Huda Taja, that contribute to this work. Thank you again.
Thank you, Hamza. Thank you for the nice presentation and all the different details that you shared with us. And yes, again, if anyone has a question to Hamza, please feel free to ask directly or through the chat room as well. Okay, we have a comment from Daniela. She said that just a comment, really interesting, the energy audit you presented. I think this kind of studies play a key role if you want to foster geothermal development. We need to analyze the profitability. Yeah, indeed.
Yes, exactly. She has right. And because when we think to introduce a renewable energy system, we have to think first to implement energy efficiency measures, because they have a very positive impact by reducing the required power capacity, and this will reduce significantly the investment required for the renewable energy systems. That's why we have performed this energy audit. And thank you for her remark.
Yeah. Thank you. Any other questions, please? Okay, so if there is no questions, we may move forward now to our last presentation, which is from Dr. Sofiane Aberkan from University of Beira. The presentation entitled The Geothermal Heating Case Study for Sena, the Thermal Spring. Sofiane.
So thank you, Abdelkader. So we will share my presentation.
Yes, please. Okay, we can see it. Yeah. Maybe just put it on the full screen so we can see more details. Okay, yeah.
Yes.
Go ahead, Sophia.
Yes, so bonjour tout le monde. Hi everyone. My name is Sofiane Aberkan. I am assistant professor at Beira University in mechanical department. I am also a member of energetic and mechanic and engineering laboratory at Gomeldas University. So today I have the honor to present to you our work, which falls within the framework of the UNESCO project, EGCP 336. So it consists of a sizing study of a heating system based on geothermal energy for the Ksana Hammam complex situated where. So this work was carried out in the form of a master degree final study project by the student Amin Agoud and Zain Abdurrahman, and in collaboration with Mr. Ajouj, director of the Ksana complex, and he is also a geological engineer. I start with the presentation of the complex of Hammam Ksana. So Hammam Ksana is a thermal site located in the heart of the Ksana forest, situated in the municipality of El Hashimiya, 34 kilometers south of the capital of the province of Guelma. So with its important hydrothermal emergence and proven therapeutic qualities, the Ksana regions offer one of the first tourist opportunities in the province of Guelma. The current sector is part of an ensemble comprising 3 units: the traditional bath units, medical units, and accommodation units. So only one could be built now, partial exploration, up to 40% of this global capacities. So you see this photos, the structures of the traditional bath units, which put into operation at the end of 2008. So figure 2, so we have 60 individual bathrooms, 2 separate collective baths for men and women with a capacity of 50 people each one. Figure 4, so we have a steam bath with a capacity of 30 people, and waiting and restrooms for taking bath. It includes also a new accommodation, which is not yet operational and is the subject of our study. So we try to sizing heating systems. So the accommodations for these accommodations, which is composed of 2 suites and 20 studios. It contains also cafeteria, restaurants with 60 seats, and outdoor rest area, relaxation terrace, and children area. The following table contains the data and particularities of the hot spring. So the temperature in the emergence is equal to 92 degrees Celsius. Volume flow rate is equal to milliliter per second. The chemical phases is sodium sulfate with a pH equal to 7.50. So the transfer is done by gravity between the spring and bath. As you can see in figure 10, it is artificial geothermal spring. Because due to the long distance between separating the complex and the hot springs, so 40 meters long channel was dug in throughout the mountains to transport the hot water. And since the location of the complex is low compared to the spring, so it only depends on gravity to transport it to the bath without using pumps. Then the hot water is transferred to the cooling tank stated in figure 11. So the cooling tanks to reduce the water temperature from 19 degrees Celsius to 60 degrees Celsius for use in hot baths. So the dimension is of this tank 6 meter length, 4 meter width, and 3 meter of height. So the objectives it works. So firstly, is the estimation of the heating needs, heating demand of the new accommodations, and the sizing of heating system using a coil exchanger immersed in the cooling tank. So the accommodation unit has an area of 800.7 meters square. It's composed of 20 studios and 2 suites. So this tableau represents architectural data of studios and suites. So the living area of the studio is 32 meters square, and for the suites is 42.85 meter square. This is for the description of the accommodation. So to calculate the heat losses, so this calculation is based on the Algerian building thermal regulations, document technique réglementaire DTR C3.2. So these losses are calculated according to the material used in the construction of the accommodation, and also depends its location. So the total heat losses are living space heated to the outside are calculated by using the equation 1. So DT is the heat losses by transmission throughout opaque walls, like floor, exterior walls, ceiling, and glazed like windows, and the thermal bridge. So we are considered for the whole building can be evaluated at 20% of the losses by transmission. The air is heat losses by air movable, either by ventilation or by filtration due to the wind throughout joints in the constructions and tracks around windows and door. So this table presents the calculation results of the total loss in each room. So that the total loss of the heat losses of this accommodation structures so are estimated around 68.5 kilowatts. For estimation of heating power, so we are taking into account the heat gain apported by the lower floor of the bus maintained at 40 degrees Celsius. So the power necessary for heating the room will be reduced to approximately 41 kilowatt, which will be received by the available power supplied by the hot water. So this available power, which is equal around 1 megawatt, exceed our needs, and was calculated with respect to the temperature of 60 degrees Celsius to don't affect and disturb the operation of the hammam. So many processes involve the exchange of thermal energy, and as such require at least one equipment capable of transferring heat between two or more fluids at different temperatures. These equipments are commonly called heat exchanger. So the general principle of heat exchanger consists in circulating of the fluids through a wall which puts them in thermal contact, and the heat exchanged by convection and convection. So in industry, there are several types of heat exchanger, such coil heat exchanger, plate heat exchanger, double tube heat exchanger, and shell and tube heat exchanger. So in our choice is focused on the coil exchanger, which will be merged in the geothermal water collection bank. So the choice of these configurations comes down to its compact structures, its ease of implementations compared to a shell and tube heat exchanger, as well as its reduced maintenance costs. For the characteristics of the helical tube or coil tube, so we consider an internal diameter of 50 centimeters, thickness of the tube 4 millimeters, and the thermal conductivity of copper tube equal to 390 watt per meter degrees Celsius. So here we present thermal analysis of heat exchanger. So we have already estimated the power of the heating by the DTR. C3.2, which equal to 41 kilowatts. So the objective here, the purpose here is to estimate, to calculate exchanger area A. So for that, firstly, we calculate the logarithmic mean temperature difference, which depends on the temperature of the two fluids at the inlet and the outlet of the heat exchanger. Then we determine the thermophysical properties of the two fluids. After we calculated the overall heat transfer coefficients, depending on coefficient convection in inner and outer tube, HEI and HO. In final, we calculate the exchange area, and after we calculated, we determined the length, the pitch, and the number of turns of the coil. So the calculation results are summarized in the following table. So the exchange surface of the coil exchanger is found 531 meters square, and the length of the coil is 3,132 meters. Therefore, it's proposed to put several exchangers instead of one, since the volume of the tank is large enough. The radiators transfer heat from the hot water to the ambient air of the room where it is installed. So a blitz tip radiator model 818 made of aluminum alloy is chosen. Temperature regime of 6550 is considered. So the 65 degrees Celsius temperature in inlet of radiator, and the 550 is degrees Celsius is the temperature at outlet of the radiator. So the number of elements is calculated by dividing so the power heating over the power of one element, which is determined from the technical data according to the data T and the model chosen. So according to the results, the number of radiators point is 27, distributed over the different rooms and the corridor. The expansion vessel is integrated directly into the geothermal heating systems. So its role are to absorb the variation in water volume generated by the temperature change and maintain constant pressure in the heating circuit to prevent it from deterioration. To measure the volume of expansion vessel, we have to calculate firstly the initial inflation pressure of the vessel to combat the static height of the building and ensure sufficient pressure at any point of the circuit. So H here is the height between the location of the vessel and the height point of our installation, which is estimated at 5 meters. Then we calculate the cold filling pressure of the installation with this relationship. Then we calculate the useful volume, which decided to compensate for the variation in volume on the primary fluid between 0 and 120 degrees Celsius. So the useful volume is equal to the volume of fluid contained in the overall installation multiplied by the expansion coefficient of water at the maximum temperature of the installation. The vessel pressure factor, it's a pressure ratio defined as follows. So where PS is the safety pressure, it's taken equal to 6 bar. The calculation of the nominal vessel volume is done by the following expressions, and it's found equal to 300 liter. In conclusion, so the case study was carried out for the heat system based on geothermal energy at a new accommodation of the Hammam Ksana complex, and this by using a heat exchanger invested in a thermal water tank, which will heat the water that supplies the radiators and thus heats the accommodations. To size our exchanger, so first we had to estimate the total heating demand for the accommodation by calculating the heat losses and gains. Then we calculated the necessary exchanger area for the coil exchanger. Now the results were that we have presented show all the interest and the attention that must be brought to the development and exploitation of the geothermal energy for residential heating. Our perspective for the next work, so the optimization of the heating system put in place by sensing with the pipes and the circulator, which allow to the proper French operation of the circuit. A technical and economic study of the proposed heating systems. So we put this year two students who works in this economic study. Also, we can integrate a parallel ORC system for the production of electricity and exploitation of hot water after its use in the bath for the heating of greenhouse. So the exit temperature of water after use is approximately 14 degrees Celsius. So thank you for your attention.
Thank you, Dr. Sofiane, for the nice presentation, and yeah, it was really nice to see the sizing of heat exchanger and the application with the geothermal sources. And again, please, if anyone has a question to Dr. Sofiane, please feel free to participate. Yeah, we do have a question from Daniela. She said, thank you, Sofiane. The two temperatures you considered to estimate the available thermal power, 90 and 62 degrees Celsius, how did you define them? 95 is the hot spring water temperature, and 62 is what, like? Yeah, she is asking about these two temperatures, how you define them.
Yes, thank you, Daniela. So the 19 degrees Celsius is the temperature of a hot spring and emergency. It's measured. And the 60 degrees Celsius, it's the temperature used in the bath. So the tank is used only for the cooling, this water from 90 to 60 degrees Celsius. So by integrating, by using the heat exchanger, we try to recuperate this energy to convert it to heat the accommodation.
Sofiane?
Yes, yes.
Did you finish, Sofiane?
Yes, I finished. Go ahead.
Okay. Sofiane, historically, temperature of Xena from 60s still now, I never seen 90 degrees in Xena. We managed to I never seen Xena 90s. From historical studies, still my thesis for the region. My last campaign for Xena is dating 2016, and I found 70 only.
From the data,
yeah, in the emerging, I never seen 90, but we managed to do the measured with the other tools, with 3 tools to see this 90 in Xena. It's between brackets. Okay.
From the data,
Xena. In
yes,
the
from data, it's straight well. Donc from data, it's Mr. Ajouj. He's a geological engineer, and he's also director of the Hammam. So he gave me this data from temperature, volume, mass flow, and others particularity and data from the springs. So we confirm with him.
We must confirm this value. It's but for me, I never seen in the Xena historically studied for 50 years. it depends. Maximum it's 70 degrees Celsius for Xena to correct, but we managed to correct in the file. Okay.
Okay.
Sorry to the intrusion. Okay.
Thank you. Thank you.
Well, not at all.
Yeah. Thank you. Any other questions? Otherwise, I have a question, Sufyan.
Yes.
Yeah, actually, one of the big challenges to size heat exchangers in geothermal applications is the how I say is the avoidable of deposition issues. So yeah, so for example, I don't know, during your calculation, I think you didn't take in consideration that there may be some deposition issue in the heat exchanger pipes. So this may reduce the efficiency of your heat exchanger. And also, sometimes if the deposition of this, particles and they may block these pipes sometimes. We have seen in our visit in Guelma, in Chellala, some pipes that are completely blocked with this deposition. So are you taking in consideration this issue during the installation of this system for this?
For the moment, we do not take into account the falling factors. So we call it falling factor to take into account the deposits of the particles in the pipes of heat exchangers. So we'll consider it for future work. Yes.
Okay. Yeah, because this is one of the big issues.
Bonjour tout le monde.
Bonsoir.
Je me présente, c'est M. Zemouli, je suis le responsable du bureau d'ERIP. Donc, j'ai plus de deux questions à poser à M. Sammari et M. Ebreken. Première question, est-ce que l'application de tout ce qui est géothermie dans la production d'électricité chez nous en Algérie, est-ce que ça reste au stade expérimental, premièrement. Deuxièmement, avec la vapeur géothermique qu'on a, les différentes stations thermales, jusqu'à quelle puissance on peut aller point de vue production. Et la troisième question, est-ce que on a réalisé jusqu'à présent même une petite centrale à vapeur géothermique, et si vous pouvez nous citer le lieu et la puissance installée. Merci.
Très bien. Donc, merci, M. Zemouli. Je rappelle, que, alors, M. Zemouli, c'est le bureau d'études qui nous a accompagnés pour la partie audit énergétique pour le site de Hammam Chellala. Et je le remercie pour ses efforts et surtout pour ses encouragements, parce qu'il était toujours là, disponible pour nous orienter, parce qu'il est le plus expérimenté parmi nous sur la partie audit énergétique. Moi, je vais répondre sur la partie électrique et je laisserai Sofiane Aberkan reprendre la question relative à la production de chaleur. Alors, pour la production d'électricité, en tout cas, nous, l'étude que nous avons menée, c'est plutôt une étude de faisabilité parce qu'il fallait d'abord se pencher sur les technologies de centrales qu'il faut déployer. Et comme les niveaux de température ici en Algérie, elles sont très faibles, donc je parle des températures des sources thermales en surface, donc généralement, on ne dépasse pas les 98 degrés. Pour les meilleurs sites, qui est celui de Guelma, dans ce cas, on ne peut pas utiliser des centrales électriques type flash. Ça veut dire qu'on ne peut pas, on s'est placé plutôt dans une configuration de récupération de chaleur. Pourquoi? Si vous vous rappelez, c'est qu'à un moment donné dans ma présentation, la température de la source thermale, elle est tellement chaude que la station thermale ne peut pas l'utiliser comme ça. Pour des raisons de sécurité, sinon on risque d'avoir des brûlures au niveau des utilisateurs. Et donc, qu'est-ce qu'ils font eux? Ils font un refroidissement à température ambiante. de ce qu'on appelle un refroidissement naturel, jusqu'à la température de 47 degrés. Et du coup, nous, dans notre réflexion, on a placé le système au RC pour récupérer cette chaleur de refroidissement qui va être dégagée suite à ce refroidissement naturel. Et donc, je récupère à partir de 97 jusqu'à 47 degrés Celsius de chaleur, si vous voulez, sur le flux géothermal. Donc, moi, j'ai travaillé sur un système de récupération de chaleur. Et d'ailleurs, c'est le cas qui a été étudié par Sofiane Aberkan tout à l'heure pour le chauffage. Alors, pourquoi on a fait ça? La simple raison, c'est que parce que nous, on a travaillé avec le partenaire, parce que lui, il a donné les données, il a mis à disposition les factures électriques, les besoins et tout. Donc, on avait des données importantes à exploiter. Maintenant, si on veut aller vers des échelles industrielles, là, il faut changer d'approche. Donc, il faut penser plutôt à aller taper l'eau dans le réservoir. Donc, on va faire une sorte de double forage, comme dans le pétrole. Hein. Donc, c'est des puits d'alimentation et des puits de production. Et donc là, on va injecter de l'eau qui va aller vers le réservoir. Elle va se réchauffer. On va la récupérer très chaude pour alimenter la machine ORC pour la production d'électricité. Et en tout cas, nous avons cette vision-là. Et d'ailleurs, c'est la raison pour laquelle M. Filali a tout à l'heure présenté le borehole, hein, parce qu'on voulait étudier le comportement des puits, comment ils vont se comporter, comment on va optimiser la récupération de chaleur dans le sol. Malheureusement, on n'a pas les données nécessaires, elles ne sont pas disponibles. Alors, on sait qu'il y a quelques institutions publiques qui ont ces données-là, mais ça reste du caractère confidentiel. On n'a pas accès à ces données-là, mais normalement, on va lancer une étude dans ce sens à partir de l'année prochaine. On va utiliser la méthode MT pour essayer justement de caractériser les réservoirs, voir son volume, sa température et surtout sa profondeur pour pouvoir choisir les sites les plus appropriés pour le forage. Pourquoi? Parce qu'un puits très profond, ça coûte très, très cher et donc on va essayer de trouver les limites supérieures du réservoir pour aller le taper là où il faut. Voilà à peu près par rapport à la question relative à la production d'électricité. Maintenant, est-ce qu'on va aller vers des réalisations expérimentales? En tout cas, nous, on travaille là-dessus. Donc, c'est ça notre objectif. Maintenant, tout dépend dans quelle puissance on veut se placer et s'il y aura des financements ou non. Et peut-être la chef de projet, Daniela Blessent, qui est la responsable du projet EGCP 636, elle est là, donc elle peut nous éclairer sur d'autres mécanismes de financement. D'ailleurs, on y parle souvent pour essayer d'aller chercher des fonds internationaux, pour essayer de financer chercher des financements internationaux pour financer ce genre d'applications pilote. Voilà. Je laisserai peut-être la parole à mon collègue Sofiane Aberkan pour rajouter la partie relative au chauffage.
Merci, M. Smari. Donc, vous avez évoqué une question par rapport à les applications de la géothermie en Algérie. Donc, à ma connaissance, pour le chauffage, ça n'existe pas. À ma connaissance, je ne sais pas il y en a des applications, mais à mon niveau, donc, pour le chauffage, ça n'existe pas encore. Moi, pour le chauffage de serre, je pense qu'il y en a des applications, mais pour les applications de chauffage, que ce soit pour l'utilisation de pompes à chaleur ou bien d'échange carrément, à ma connaissance, ça n'existe pas. Donc, ce qui a poussé à travers ce projet, à travers notre participation, c'est de promouvoir les applications géothermiques. Donc, comme l'Algérie, on a un potentiel très important. On a à peu près 262 sources thermiques, donc qui sont utilisées juste pour des besoins traditionnels, comme hammam, mais on n'a pas réfléchi ou bien on n'a pas allé chercher des applications réelles qui vont nous permettre de soit produire l'électricité ou bien de produire du chauffage. Et je tiens à remercier, vous permettez, donc entre parenthèses, à M. Adjouch, qui nous a donné l'opportunité de travailler dans son complexe. Donc, comme c'est un ingénieur et géologue, donc il a un peu l'esprit ouvert pour toutes ces applications nouvelles. Donc, il tient à que les études soient menées, soient plus tard, Inch'Allah, réalisées. Donc, on a commencé par des études de faisabilité, des démonstrations préliminaires, mais on essaie d'y aller, Inch'Allah, vers la réalisation. C'est tout celui qu'on
Oui. عبد القادر
Yes, yes.
J'étais monsieur la cassette de monsieur. J'ai oublié.
Okay, go, Monsieur Aitouali. Then I will come to you, Fouad.
Je vais rajouter un complément
Yes.
sur les deux collègues, Hamza et l'autre, deuxième, Sofiane. Cher Sofiane, normalement, il y avait, pompe à chaleur, il y avait une étude expérimentale du CIDUR il y a quelques années. Docteur Bendeikha a fait pompe à chaleur dans la région Saïda. Juste une étude expérimentale, pompe à chaleur, chauffage d'une école primaire à Saïda. Et CIDUR, il y a plus de 5 ans ou 6 ans cette étude. En plus, je complète sur monsieur Hamza. Pour l'ICT, c'est la région Guelma, vu que le flux de chaleur il est important, le gradient est très important, donc logiquement, avec une étude, une bonne étude MT et un bon modèle conceptuel et dynamique, on peut pas faire notre forage sur l'anomalie, elle n'est pas loin, hein, elle n'est pas loin Guelma. Je crois, elle n'est pas trop profonde. Pour ça, il faut qu'on dise ça aux futurs sponsors. C'est-à-dire,
Oui, c'est Lyonna.
C'est-à-dire les séduire. Alors,
Ah oui, c'est effectivement.
La séduction, d'accord. Avec tous mes respects, c'est ça. C'est-à-dire, on a préliminairement également, on a un bon potentiel, pardon, c'est pas potentiel, bon, on n'arrive pas. On a un bon gradient, un flux. Donc, deux ingrédients qui nous donnent plus tard, avec une bonne MT, magnétique tellurique, c'est-à-dire voir l'anomalie et voir le réservoir. Attention, source, c'est comme pétrole, voir la roche-mère ou aller au réservoir. C'est-à-dire on cherche d'avant tout l'anomalie, d'où vient après ou le réservoir. Si on arrive à caractériser ces deux choses, la région de Guelma, donc le forage, je pense que c'est pas trop profond. Hein. Ça ne sera pas trop profond. Hein.
Thank you, Dr. Aitouali. Fouad, you would like to say something? Yes. Fouad?
Oui, Abdelkader, oui.
Yes.
Oui, Abdelkader. Concernant c'est la même remarque, c'est-à-dire c'est la même la même remarque concernant l'exploitation de l'énergie. Il existe l'exemple de Saïda à l'école où il y a où il y a c'est la production d'électricité plus le chauffage. Mais d'après mes connaissances, parce que j'ai informé avec quelqu'un, j'ai informé avec quelqu'un de la région, c'est-à-dire le site, c'est-à-dire le dispositif est en arrêt parce que la source, c'est proche, c'est-à-dire on partage avec le hammam le plus proche. Donc le propriétaire il a arrêté c'est-à-dire la source elle-même sur l'école. Donc le projet, soit le chauffage, soit l'électricité. L'électricité, c'est-à-dire c'est pas important pour l'école, c'est le chauffage beaucoup plus. Il existe tout un article sur Elsevier. Je ne sais pas, j'ai oublié l'auteur. Oui, oui. C'est-à-dire, il y a des photos de dispositifs, de la chaîne, toute la chaîne et tout. Donc, c'est ça. C'est juste ça.
Merci.
Okay. Thank you, everybody, for the comments and the answers. Is there any further questions before we close this meeting and panel presentations? So just to say that Daniela commented about what Hamza said about the financial. She said on envisage chercher des sources de financement international pour développer des projets, puisque le programme IGCP donne juste l'appui pour organiser une rencontre annuelle, pas pour mener des travaux, bien sûr, de recherche. On behalf of the IGCP group, I just want to thank the organizers, the speakers, and the attendee. Really nice and interesting session. Many thanks to the Algerian team for sharing their work and research. We would like also to thank you, Daniela, and thank everybody here, the presenters, the attendees for these interesting talks. and it is our pleasure to it was our pleasure to present what the potential of Algeria is, and sharing it with everybody around the world. So just for your information, that this panel is recorded, and we will share the link of the recording that can be, shared with everybody who is interested in geothermal resources in general, and particularly in Algeria. So thank you again, everybody. We wish you a nice evening, nice day, or maybe nice night if you are around the world. Thank you again.
Okay, thank you, and see you soon, and
yeah.
Stay in touch.
Yeah, see you. Thank you.
Ciao.
Thank you.